Online shoppers typically string together a few words to search for the product they want. But in a world with millions of products and shoppers, the task of matching those unspecific words to the right product is one of the biggest challenges in information retrieval. Using a divide and conquer approach that leverages the power of compressed sensing, computer scientists from Rice University and Amazon have shown they can slash the amount of time and computational resources it takes to train computers for product search and similar extreme classification problems like speech translation and answering general questions. In tests on an Amazon search dataset that included some 70 million queries and more than 49 million products, the researchers showed their approach of using merged average classifiers via hashing (MACH) required a fraction of the training resources of some state-of-the-art commercial systems. Product search is challenging, in part because of the sheer number of products. There are about 1 million English words, but there are easily more than 100 million products online. There are also millions of people shopping for those products, each in their own way. Some type a question, others use keywords, and many aren't sure what they are looking for when they start. But because millions of online searches are performed every day, tech companies like Amazon, Google, and Microsoft have a lot of data on successful and unsuccessful searches. And using this data for a type of machine learning called deep learning is one of the most effective ways to give better results to users. Deep learning systems or neural network models are vast collections of mathematical equations that take a set of numbers called input vectors and transform them into a different set of numbers called output vectors. The networks are composed of matrices with several parameters, and state-of-the-art distributed deep learning systems contain billions of parameters that are divided into multiple layers. During training, data is fed to the first layer, vectors are transformed, and the outputs are fed to the next layer, and so on. Extreme classification problems are one with many possible outcomes and thus many parameters. Deep learning models for extreme classification are so large that they typically must be trained on what is effectively a supercomputer, a linked set of graphics processing unit GPUs, where parameters are distributed and run in parallel, often for several days. A neural network that takes search input and predicts from 100 million outputs or products will typically end up with about 2000 parameters per product. So the final layer of the neural network is now 200 billion parameters. It would take about 500 gigabytes of memory to store these 200 billion parameters. It will need 1.5 terabytes of working memory just to store the model. The best GPUs out there have only 32 gigabytes of memory, so training such a model is prohibitive due to massive inter-GPU communication. MAC takes a very different approach. The researcher describes it with a thought experiment, randomly dividing the 100 million products into 3 classes, which take the form of buckets. That is, mixing iPhones with chargers and t-shirts all in the same bucket. It is a drastic reduction from 100 million to 3. In the thought experiment, the 100 million products are randomly sorted into 3 buckets in 2 different worlds, which means that products can wind up in different buckets in each world. A classifier is trained to assign searches to the buckets rather than the products inside them, meaning the classifier only needs to map a search to one of 3 classes of product. In their experiments with Amazon's training database, the researchers randomly divided the 49 million products into 10,000 classes or buckets and repeated the process 32 times. That reduced the number of parameters in the model from around 100 billion to 6.4 billion, and training the model took less time and less memory than some of the best reported training times on models with comparable parameters. Mac's most significant feature is that it requires no communication between parallel processors.